thank you very much. Good morning, everyone. My name is Steve Albrecht. I escaped the Berlin winter and I came here. I'm very happy to be here. Thanks for the organizers to invite me to this great conference. So we change gears a bit and we dive now deep into the, maybe not so deep, into the material science and device physics of perovskite multi-junction solar cells. There had been great talks yesterday that introduced the concept of tandem solar cells and also the concept and the different device architectures of perovskite solar cells. So that saves time to me and I can dive deep or quickly into the motivation. So why do we work on tandem solar cells? In Berlin, we took the decision like 10 years ago to work on tandem solar cells, and we have drawn this figure on the left side around 2017, so like 8 years ago. And our vision at that time was that we have nice increasing single junction efficiencies, but of course they will top up at some time. And when we are able to use the high efficiency potential that a tandem solar cell has, because it utilizes the sun spectrum more efficiently, less thermalization, more coverage of the sun spectra, then we have a higher efficiency potential for tandem and triple junction solar cells. And then of course, if you industrialize this technology, then we have modules out there which we are having by today. Right, so on the very right side, you see a figure that summarizes the efficiency increasement over time for perovskite on silicon. So by today, we know that we are at, or let's say the best cells are about 35% efficient, but 5 years back, there was a strong race, and it was very important to show that efficiency improvement for the technology drive. And we are happy to have also taken part in that race. So we had 3 different independently certified world records in our center in my team. The first one here, back in 2020, we introduced so-called self-assembled monolayers or molecules, so-called SAMs. We also heard them yesterday. And what you see is that all of the upcoming, or let's say most of the upcoming record cells from also different centers or companies, they also take and use those self-assembled monolayers as a contact material today. So this has been, let's say, something that took over. The second thing that we introduced was periodic nanostructures. In that point, I was very close to the 30%, this psychological barrier that we did not overcome by that time in the certification. But what we also did is we included a optical refined backside of the wafer, and this is also, especially in the KAUST records, that's included now. So again, something that took over in this community. And last but not least, this one here, 32.5%. What we did there is we did a surface treatment, a so-called passivation of the perovskite surface in order to get a better film, or let's say a less recombination at that contact, and with that we could have a very high open circuit voltage, which is still among the best today. All right, so that's efficiency, but of course we understood from yesterday, and we know in the community that stability is something very important. So how about stability of those cells? So we're looking into a literature survey now that is maintained efficiency after a certain time. So how much efficiency can those tandem solar cells maintain after a certain time? And it is color-coded in year of report. So we start 2020 was the first stability measurement reported, so it's not very old data, of course. And you see, over the course of the last 5 years, we are getting higher efficiency for a longer time. This is what we want to have, right? But of course, we want to have very high efficiency for decades and not just 1,000 hours under constant MPP tracking with 2,000 hours in the lab. So right, that's something very important. That's also a motivation for my presentation today. Recently, we have shown, at least for single junctions, so only the perovskite in the bad Berlin winter condition, that it's not so bad. So what you see here is the longest outdoor data that there is in literature, which we have recently published. So this is over 4.5 years of a perovskite single junction in our condition, in our climate condition. Credit here goes to Caro, a colleague from Helmholtz and Berlin. So what you see is we're taking indoor measurement, then this is 2 different cells going outdoors, and you see a summer-winter variation, so Berlin winter really is bad and our solar cells don't like it. But what you see is if you take the summer peak, then it's not so bad. So first 2 summers, nothing is happening. And then there's a short, let's say slow degradation over the time. So I think that's very promising data. And if you look at the structure here, then you realize there's bromide in it, a significant fraction, which is not known to be very stable. So there is a high potential, that's what I'm showing here, for those solar cells to be included in tandem structures. All right, with that, I come to the outline. So I said I want to dive into material science and the device physics. So I have 3 different, very recent scientific, let's say, projects that I would like to share with you. They are at the stage to be published, so that's brand new scientific results from our labs that you will see now. So the first one, we'll talk about material as a new electron selective contact. So typically the fullerene C60 is used there, but we have a new molecule. I will also go in the second chapter about co-evaporation of the perovskite, so how to form the perovskite. Typically solution processing is used, that is very quick and cheap, but there's a way to co-evaporate them. I will tell you what we did there. And last but not least, if I have time, then we'll come back to our nice self-assembled monolayers molecules for all perovskite triple junction solar cells. All right, so let's start with the first topic. So I said we used the C60 fullerene that's shown here. It's a very nice molecule, especially if you work with organic solar cells, then this one is there for decades, and it's very interesting. However, as you see, there's this very strong motivation to get rid of that molecule in a perovskite solar cell. It is expensive, at least compared to the ingredients for the perovskite, and it has a couple of other disadvantages. So some is mechanical stacking or mechanical integrity is not very high, so the interface with the perovskite with that molecule is very soft. You do see photoluminescence quenching. That means your solar cell, if it's in contact, or let's say your perovskite, if it is in contact with that material, doesn't emit light, it's not a good LED anymore, and then it's also not a good solar cell anymore. We did find that there's some trap states formed, especially if you process everything in air, which you want to do in your production facility at some point. You don't want to fill your fab with nitrogen, and it also absorbs. And especially in a tandem solar cell, that's very relevant because the light first enters through the electron selective contact and then is absorbed in the perovskite, so you want to get rid of the absorption. We and the community has been working for quite a while on replacing the C60. However, so far there's not a nice material out there until very recently. With colleagues from Lithuania, we came up with this molecule. Looks very fancy, and you might think now, why this molecule? So there's literature before we started of those nice carborins. And there's also literature about molecules that have a conjugation and distermination, like this one. And we tried first starting with molecules that were out there in literature, and we found out by ourselves that they were not working, at least not for our perovskite, our dedicated tandem-like perovskite composition. And then in certain iterations, we came up with this molecule and also with derivatives in the same family. And now, since I'm talking about it, it has very good properties in a perovskite solar cell, and especially for the application in tandem solar cells. So first of all, about absorption. So I said that it does not need to absorb. So what you see here is the absorption coefficient. The new molecule is the red data, and C60 is the standard, is the blue data. And you see it has a wider band gap, so there's no absorption in that region. And also the absorption coefficient by itself is much lower. And in addition, you can make a thinner layer, so 3 factors making a stronger reduced absorption loss. Then what you see here in this bar chart is the quasi-Fermi level splitting, so that's the charges that remain in a solar cell with the one or the other contact, and of course that needs to be very high for a solar cell. And with the new molecule, you don't have that PL quenching, so your solar cell is still a very good LED, which you want to have. And then on this figure here, so-called SPV, that's surface photovoltage, that's a very dedicated measurement that was developed by colleagues in our center. And what you see there basically is you hit your sample with a laser pulse or with an illumination, and then you can track how charges separate, and then they build up a voltage, and that's what you see here. So in your transient, what you want to have is you want to have a strong signal. That means you have a separation by itself, and you want it to be very quick, and you want it to have it in the right direction, so that charges go into the right direction. And comparing C60 and the mu molecule, you see by itself, charge separation is a bit stronger. However, if you zoom into that transient early time, then you see the rise time is a bit smaller, and that has a reason which I'm coming to in a bit. Okay, so if you look at this molecule structure, you can think about, okay, this is a very complex chemistry. We did cost calculation, so it's in the film, it will be cheaper. The molecule by itself might be a bit more expensive, but if you use less of the material, the film will be cheaper. But we also did a single component analysis, made solar cells only with the single components. And what you see is that especially only the carborane doesn't show any photocurrent at all. So it's just a line here. And this molecule works, interesting, it works, but still you see the JV curve here, the fill factor, and also the VOC slightly reduced. So it's working, but it's not giving a performance that you would need. So you need, let's say you need the combination of both. All right, so as I said, we put it in tandem solar cells. So here's results on tandem. So first let's look at the right plot. That's EQE, and especially here in that wavelength region, you see a higher EQE for the new molecule compared to the C60. That's because of less absorption, and that amounts up to, where is it written, 0.8 milliamps per square centimeter, which is quite a lot for a tandem solar cell. And since also in the JV curve here, since also the new molecule has less recombination, you have a higher VOC and much higher efficiency potential. I'm pretty sure that this molecule will also enter the community and show high results very soon. Okay, so what about stability? So we also did measure stability, especially mechanical stability of the new molecule. So what we did is we tried to measure the force in which you rip off that interface, this one here. And you see that the new molecule, I mean, it's not much higher, but at least it's a couple of 10% higher. And in terms of scan stability, at least that's short-term stability, not like long-term decade tracking outdoors. You see that typically you use what we call pyrazinium iodide interlayer to get the very best efficiency, and you see there's a trade-off in scans, consecutive scans, that you don't have in the new molecule. So we are confident that also higher stability is given with the new molecule. All right, so that was the first part. Now coming to the second part. So now we move away from the material that is used as charge-selective contacts into how the perovskite is deposited by itself. And there's a lot of, let's say, a lot of motivation why you want to co-evaporate the perovskite. Let me go quick here. So you know that silicon has a certain texture, and you can see that here. So that's that's an SEM image of like a typical silicon texture. And the perovskite, if you form it from solution, and it's very hard to have a conformal growth. So with co-evaporation, you can do that. Also, co-evaporation, or let's say dry processing in general, is something you can scale up very easily. And recently, also very high efficiencies have been realized. However, there's also a drawback for that method, which is especially reproducibility is something that is not yet given. So the community is much smaller. So within the large perovskite community, there's a small co-evaporation community. And this community has not yet reached a full process control. So understanding how the process is working and thereby also trying to get higher reproducibility. And that's something we have worked on. So first I show you how bad reproducibility can be. So what you see here is SEM cross-section image of perovskite films. So this is a film that looks very nice. So you have grains that go from all the way the bottom to the top, and they are large and they're homogeneous. So this is how it should be. And within the same run, you don't do anything differently than placing samples at different places in the chamber. You see small grains and a very different morphology. So this is how bad it is. However, of course, we have a solution to that problem, and also others in the community have a solution. So what you could do is you could form a seeding. So you have a layer first, and then you put your perovskite on top, a bit like epitaxial growth. It's not the same, but it's going into that direction. And if you form the right seed layer, so we go for a single component seed layer that you can evaporate first, very thin, 5 to 10 nanometers. It's not a complete closed film. It's just like a catalyst at that surface. Then you go to films that are very, very nice again, and they have a much smaller spread that you can also see here. So here's optical properties, the band gap of those films, and you see there's a spread. This is what you don't want to have. If you do form the right seed, then you have the perfect band gap for a tandem solar cell, 1.68, and the spread is much lower. Don't want to go into the details here or the other properties, but also in the quantum efficiency, you see that band gap change. You don't see any sub-band gap absorption property or any halide segregation, which for some cases you do see here. So you see a double emission peak. This is what you don't want to have. If you do use the correct seed layer, then this is going to be right. Okay, we can implement that into single junction solar cells, so only using the perovskite, the co-evaporated perovskite with a seed layer, and then you see the results here. So you're getting roughly 18 to 20% efficiency. That's quite good for that band gap and for the technology. And you see the spread in efficiency as compared to the standard is much reduced. That's what you want to have. And if you do everything right, then you can also have a stable output that's 1,000-hour tracking at room temperature, but we also have very nice data for 90 degrees, so that's accelerated lifetime testing. So we're very confident that co-evaporation has a very good benefit in terms of stability of the perovskite. All right, so then we have, in Berlin, we have a synchrotron, so that provides very nice measurement opportunities. So we used it and tried to understand a bit better the initial growth. So what you see here now is microscopy or microscopic elementary resolution of, especially of the very first growth, the very first nanometers of the perovskite. So we do an elemental mapping in order to understand how the perovskite is growing and why the seed layer is improving the growth. So coming back to our SAM layers, here what we see is we see we see bright spots, very dark ones, and let's say grayish spots. So that is our self-assembled monolayers or not monolayers that form various different heights at the surface. So you see a very thick layer here, a very, let's say, medium and a thinner layer here. And that also then tends to different growth of the perovskite on top of that different layer. So it's very sensitive to what is underneath. So you see here that the carbon is changing, and we also have indium signals showing that the ITO, the TCO, let's say the transparent electrode underneath, is showing through that regions. So now if we form a seed layer first, then you see it's much more homogeneous. So even if the seed layer is 5 nanometers in this case, or 10, it's not a closed layer, but it does form a much better perovskite to start with. So the initial growth is improved over time. Now it becomes even maybe a bit more tricky in terms of the measurement, but what you see here is you see the emission of the perovskite from that buried interface. So what we do is we first evaporate the perovskite, then we rip apart, so we peel off the perovskite, and then in the electron microscope we look at the emission cathodoluminescence in a filtered way. You see a lot of blue here for a no seed layer, and you see, let's say, the true emission for the one that has the seed layer. So here, what we know is at this wavelength, there's a lot of lead iodide, which you don't want to have. So that's a decomposition product, or let's say it's a product that is not reacted. Here, everything is fine. So this is what you want to have. This is what you don't want to have. And then we can come to the scheme here, and we know that we do have a non-monolayer of our SAM. This is our SAM molecules, and we know that we have thickness variations and all kinds of unsorted film arrangements. If we don't do anything about it, we have lead iodide, which we don't want to have, and then we have a bad film. If we put a seed layer on top, let's say everything becomes better, and then we can have a very nice growth, very homogeneous growth, as you can see here. So again, this is SEM images of the bottom side of the perovskite grown on top of now textured silicon. You see here without a seed layer, it's very hard to see, but grain sizes are very different. With the seed layer, they're very good, very homogeneous. And then, of course, we can implement that into tandem solar cells. So here, this is fully textured, conformally grown tandem solar cells. You see an SEM cross-section image here. So this is the perovskite layer, fully conformally grown on the pyramids. And if you do everything right, then with the seed layer also, this efficiency is higher, and the spread, again, is much reduced. And we have an independently certified efficiency of close to 30%, which is a record for that technology and using co-evaporation. All right, so last but not least, the third part of my presentation. So now we go into all perovskite solar cells. So there's a strong motivation maybe to use all perovskite solar cells in space. They have been shown to be very space stable. So if you hit them with protons, they're much more stable than silicon. They also, I mean, one example is that you don't need to have high temperature processing, so the overall CO2 emission is strongly reduced. If you go to a multi-terawatt scenario, then the absolute amount of CO2 emission and energy savings you have is very important. So that is a motivation to work on it. Don't want to convince you that is something very important, but we think it is. And there's a drawback if you look into the literature, then typically people use so-called PSS, which is it's a very nice material. It's typically used for anti-static coating. So if you peel off a foil from a screen, then very likely there is PSS on top of it. However, it has some drawbacks, as I said. So again, it's absorptive. It is very acidic. It has a very strong recombination if in contact with the perovskite. However, if you look in literature, so you see out of all the published data for all perovskite multi-junction so far, over 90% uses this material because it's at least initially working and giving high performance. Right, so we have spent some years to let's say, replace that material for obvious reasons. We used this self-assembled monolayer molecule here in order to have a better hole selective contact. And also important to note is for most of the low band gap, the tin lead mixtures, perovskites, you use certain additives. That's because the tin and the lead, they have different crystallization kinetics. In order to, let's say, homogenize or get rid of it, you use thiocyanate additives. Now, if we use the additive, and if we use the new molecule, you see a film like this. This is, again, an SEM top view image. It has very homogeneous, very large grains. So it's very good. It's almost a perfect film. So you would think, okay, also your solar cell made with this additive and with this SAM is very good. Then you can, again, measure the PL. So you can look how good an LED your solar cell is. If you do that with the additive, the value is very high. So here's the SAM contact with the additive. The value is very high. However, if you then measure a solar cell, then you get JV curves like that. This is what you don't want to have. So it's a very bad solar cell. So everything looks like it's very good. It has to be very good, but the solar cell in the end is very bad. So we dived a bit deeper and used, again, photoelectron spectroscopy to understand why, in principle, the film looks so good, the PL is very high, but the solar cell is very bad. So basically, what you can see is we track the bromide because that's in the SAM. And it's the element that we track. Basically, what we find as a summary is if you use the additive, you peel off, or let's say you resorb the self-assembled monolayer and the molecule at the bottom, and you bring it to the top. And if you do so, then you have a very well passivated perovskite that has the whole selective contact on both sides. So this is not, it's not a very good solar cell anymore. It's not a diode anymore. And that's why the solar cells aren't working. All right, so we came up with a conclusion. So basically, you have two options. Either you change the molecule, the SAM, to bind it stronger to your surface, so you change the chemistry, or you change your surface, and that's what we did. So we changed the binding affinity, and by using graphene oxide underneath. So now the same molecule, here's the phosphonic acid binding group, has more OH groups and has a stronger binding, and now is less sensitive to the additive that you use, and you can get a higher film quality without penetrating the molecules to the top surface that you don't want to have. All right, don't want to go into the details here. So we use that approach to form all perovskite triple junction solar cells. So now it's a triple cell made of 3 different perovskite components. That's a very nice thing about the perovskite. You can tune the band gap in order to have a band gap, or let's say current matching. So we have a 2 eV, 1.5, and 1.2 eV band gap. And here in that layer stack, we either use the standard PSS or the new approach, the bilayer graphene oxide and the SEM on top. What you see is you get a higher current. That's what you expect because you have lower losses, and you also get a very high VOC potential. The JV curve, the electrical measured JV curve is here. This is above 27%, which is very good. But what is the most striking result here is the stability, which with the new bilayer approach is much higher compared to the PSS because it's not so acidic, etc., etc. All right, so with that, I'm at the end of my presentation. Before I go to the conclusion, I want to thank my group members. So I started with the work on the ETL side that's worked by Leah. Then I moved over to the core evaporation, which is done by Marcel, Victor, and Steffi. And last but not least, the triple junctions, which is done by Yonghoon and Kevin. And since after the presentation and after the conferences before the next conference, I also want to advertise that we're doing a Tandem PV workshop next June in Berlin. And with that, I'd like to thank you for your attention.
Thanks very much, Steve. We are running a few minutes late, so I'm just going to take one question. Someone got a really good, insightful question for Steve. No pressure. No? Oh, yeah, one question here, thanks.
So thank you very much for that. I was just really interested in your carborane compounds which had the fluoridines attached to them. So you've got 2 fluoridines. You talked about absorption, which of course is important, but you also put a layer down. Have you measured the mobility of that layer, or is it so thin that everything just tunnels through it?
Yep. Yeah, very good question. So I talked about this rise time in the SPV. So the mobility is 2 orders of magnitude lower than C60. It's in the same range of PCBM maybe, so it's 10 to the minus 3 volts second per square centimeters. We do see a very clear dependency on the layer thickness on fill factor. So we think mobility is limiting here. So that's why we have a 4 nanometer layer thickness in that vertical transport. 4 nanometer mobility is not limiting, but for the next generation molecules that we try to develop with the chemical colleagues, we look at specifically at the electron mobility of that layer. Yes, very good point, yeah.
Okay, great. We're going to break for morning tea. After that, we're going to go into the industry sessions. One logistics things I forgot to mention earlier is that if after dinner, that one bus will be coming back to UQ. I'm trying to organise for it to have a stop at the Essence Apartments staying at. So with that, we're going to complete the session. Please join me in thanking all 3 of our plenary speakers this morning.